Hello Energy students, Dr. John Schragi here, and I'm ready to talk to you a little bit about correlation statistics. Remember, that's one of our paired data ways of describing data, what's going on in data. And we're going to be doing a lot of stuff involving correlation in the next projects and so on. So I want to at least nibble at it. And it's going to turn out, though, that at least based on the way this data set is formatted, it turns out to be a lot harder than you might think. Which is weird because Octave has a built-in correlation function. It's called core. And, you know, like for example, if I have two one-dimensional arrays, something that has just rows or just has columns, and I have stored my data in one called X and one called Y, as long as I have, you know, two arrays that are the same size and the values match up, core X comma Y will work just fine. It'll compute the correlation just fine. For that matter, if I have my data stored in an array that is multi-dimensional, you know, that has multiple rows, columns to it as well as rows, as long as I have like one data set in column 1 and then another one in column 2, I can actually compute the correlation of column 1 to column 2 in that data set using core just X, where X is just that array. This seems slick. It really ought to work just fine. But it turns out it isn't because of some issues associated with missing data and some issues associated with how we have to make the data match up. How do we make sure that this day's data matches up with this day's data and so on? Let me show you what I'm going to do here. Let me give you an example that's very related to what you do in Project 2. Let's say we want to correlate the daily high temperatures in January at two stations. One will be Howells and one will be Hershey, just to have chosen two stations that I know have pretty good data records. So what I want to do is I want to pull out of the database all of the observations of high temperature for each of the days in January out of our 10-year data set, and I want to see how they correlate. If it's warmer than usual in Howells, is it warmer than usual in Hershey? If it's colder than normal in Howells, is it colder than normal in Hershey? And so on, okay. Now, I'm not going to show you the beginning part of how this project would work. I mean, you're going to have to use your database operations and logical indexing to compute, you know, to remove any data that are missing, and for that matter, to clean it up by getting rid of everything but January. Okay, because I mean, this particular problem, I just want to know January's correlation between Howells and Hershey's low temperatures, or high temperatures apparently. Okay, now I've got this kind of cleaned up data set. It's got no missing values anymore. It's got it's only got the January data. And I could then use my logical indexing to do another database operation, extracting just the data for what I'll call Station A, which will be Howells, filtered then for Station 506 as it happens. And I'll do the same thing again, you know, take my clean data set that's just January, and I'm going to filter out just the stations that are at Station, just the observations that are for Station 25, which happens to be Hershey. So I've made one that I'm going to call Station A and one I'm going to call Station B. And I've got the A data in one array, and I've got the B data in another. And this will happen just like that in Octave. Okay, once you have been experimenting with these logical indexing database operations, you're going to be fine getting this done in no time. So you've got this data A. And data A is an array that stores all these rows of data, which are all the observations that are good, and in January, and at Station 506, namely Howells. Over in station array data B, you're going to have all these rows and columns of data that are good, and January, and Station 25, or Hershey. Okay? Perfect. I now have just the data that I want. And in both of those arrays, data A and data B, column 5 is the high temperature data for that day. So it sounds like all I got to do is to make the correlation would be to just take the correlation of something like this, where like R is equal to the correlation function core of, okay, now there's two arguments here, separated by comma. One is a column of data from the array data A. It's going to be all rows, column 5, the high temperature data from our data A, you know, good January observations from Howells, and comma, data B, where it's all rows, column 5, the high temperature data for data B, which was good data from January from Station 25, which is Hershey. Man, this just looks brilliant. This there's be no problem. And if we actually try it, though, we're going to have a problem. Here I have a screen capture from inside of Octave where I just did the whos command to see what all I've got. And I just want to draw your attention to two of my arrays here. I have data A and data B. And oh no, my two arrays are not the same size. Uh-oh, I have more values of data A from Howells than I do from data B in Hershey. What went wrong? Well, actually I can do some displaying of some of the values that are in data A and data B to show you what went wrong. I mean, if I just display, look what this says here, display data A, row 200, all columns. 200, comma, colon. All, row 200, all columns. Look what I get. Station 506, 2011, January the 14th. High temperature was negative 6.7 Celsius, low temperature was negative 17.8 Celsius. Great. So the 200th row of data, I just pulled 200 as one to try, in data A corresponds to, that works out to January 14th, 2011. Let's do the same thing with data B. I'm going to display the 200th row of data B. Now remember, I want these rows to match up, right? I want to, when I'm computing the correlation, I want to be comparing row 1 of, value 1 of the first data set with value 1 of the second, and value 2 of the first data set with the value 2 of the second, all the way down through the whole n pairs of observations. But look what happens if I try to display row 200 of data B. I get that station 25, the year is 2013, the month is January, the date is the 12th. Oh no! The 200th row of data B from Hershey, Nebraska corresponds to January 12th, 2013. I'm off by a little over 2 years. Oh no! Well, the problem is there's some missing data at Hershey. Hershey wasn't always there when Howells was. So when we made a list of the observations from Howells, we got 310 observations, which by the way, let's see, there's 31 days in January. It's a 10-year data set. 31 times 10 is 310. There must be no missing data for Howells in January. Whereas we only had 250 observations for Hershey. Apparently 60-ish times there was no observation for Hershey. Oh no, either data problems or coding problems or data quality control problems, or maybe the station closed down. Who knows? Who knows? Well, how the heck are we going to fix this? Now we have two data sets, they're not the same size, they don't match up. The 200th row of 200th row of data set A is not the same as row 200 of data set B. We got to find a way to fix this. It is not easy. It is instructive how it's not easy. As we learn more about working with large data sets, we're going to find out that certain things are just really complicated to fix. And this is an example of something that's going to be fairly complicated to fix. If I were fixing this by hand, if I were just sitting down, with notebooks of data, what I would want is a calendar. I would fix this using a calendar. What I would do is I would take out like a 10 years of calendar, okay, and I'd make sure all the little squares are empty, and then I would go through the data for Howells. I would go through and say, okay, January 1, 2005. Yep, you got a value here. I'd put that on January 1, 2005. And I'd do that for January 2, 2005, and January 3, 2005, and I would be putting in values on the calendar. And then I eventually would get to January 31st, 2005. Put that on the calendar. Okay, now the next day is February 1st, 2005, but we don't have that because we filtered it out. So all the way through the February, the March, the April, the May, the June, July, all those squares would stay empty. Until I got all the way back to 1 January 2006. And then I would say, look, I got that observation, I'll put it onto here for 2006, and I would fill in all the Howells data onto those squares, right? Most of the squares are empty because we don't have February, March, April, May, June in this problem, but some of the values are in there. Then I would go through and do the same thing for Hershey. I would take all of Hershey's data, if I were doing this by hand, and I would take Hershey's observation and say, okay, that's an observation on the 15th of January 2008, or whatever the date is, and I'd fill it in, and I'd fill it in until I had on through all of Hershey's data, and I'd fill it in its calendar. Then I would be able to look through this calendar and say, look, lots of days we have no data at all because it's like in February or March or April where we're not even using that data in this problem. And some of the times in January we don't have both Hershey and Howells, but sometimes we do. Let's just use those dates. Okay, can you see how I would do that? I would have these calendars, and now I can see that on some of these days I do have two values, one for Hershey and one for Howells. That's what we need to reproduce, that thinking. Now, how exactly are we going to do this? What would be the computer equivalent, the Octave programming language equivalent of a calendar? Well, I made you an array that is in the data ERG 301 Nebraska directory. It's called juliandays.mat, and you can load juliandays.mat in your program, and you'll get an array called dates. And it's a pretty nifty little array. It has 3,651 days in it. Each one is a row. The first column is just an integer. I'm just counting as I was going along. But then the second column is the year, the third column is the month, and the fourth column is the day. And it's just a calendar, okay? It's just an array that just shows me, here's a date, 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 all the way down through 10 years. So now, thinking again of my analogy of working with a big old stack of calendars here, what I want to do is I want to create a calendar that's going to be associated with our data set A. Calendar isn't a data type, I'm just using this as a term. That's my name of my variable, it's my name of my array, something like that. It's going to be associated with data A, and it's going to have this same number of rows, 3,651, and it's going to start without being blank. By being blank, in the context of this, what I mean is let's put in missing numbers in there. Negative 999.9. Let's just put them in there. Let's make the whole thing have these negative 999s in there. Sorry, I forgot to turn off my phone. Alright, what I'm going to do then is I'm going to go through every observation in my data array, the observations of high temperature in Howells as it happens in January. I'm going to go through and I'm going to notice, okay, column 2 gives me the year. For every row that I'm in this array, column 2 gives me the year, column 3 gives me the month, column 4 gives me the date. Let's take a notice of that. Let's pay attention. This observation goes to this year, this month, and this date. Then what I'm going to do is I'm going to go through this dates table here and find that one. Which row in this table has the same year, month, day? Because that'll tell me, okay, apparently in my calendar, let's just say that my year, month, and day right now is January 17th, 2005. Alright, I'm going to scroll through here and I'll see, oh look, when I get to the 17th row, my year will be equal to this year, my month will be equal to this month, and my day will be equal to this one. So apparently 17 is the row this one belongs in. I'll show you an example of how to do this in just a little bit. But I'll just set on my calendar underscore A, I will set in row 17, I'll put my current high temperature in there. That's pretty slick. It's also really time consuming. You'll be surprised by how slow your little Octave program is going to run. Okay, there are undoubtedly better ways to do it, but let me show you how I did it. Okay, that kind of uses the lowest common denominator of tools that we've seen so far in this class, okay? There are fancier ways and fancier database operations and fancier logical indexing and things like that we could have done, but we're not. We're going to keep this in a more generic, this would work in C, this would work in Pascal, this would work in BASIC, this would work in NCL. We can make this trick work for lots of things. So let me show you exactly how I'm going to do it. This is the same slide we saw before, but now I've got this kind of white window on the top with some sample code. How am I going to create, okay, one of the steps I said is let's create this calendar for data A. Well, you want it to have the same number of rows as this dates array does, because there's going to be one value for every row on that calendar. There's probably much better ways to do it, but I actually liked this little hack that I did here. I just said make your calendar A equal to all rows of the first column. Okay, so we just got to, however many rows, 3,651 rows by one column. And then to make them all equal to negative 999, I just took it and multiplied it by 0 and then subtracted 999.9. I suspect that is not the best programming, but it works, okay? Ta-da! Now my calendar A is just full of negative 999s, okay? It has one for every day in the 10-year database, a negative 999. We're now going to cover some of those negative 999s up with a new value that is the observation on those days, but we got to get there first. Alright, now I'm going to be kind of showing you what the algorithm looks like here. What I want you to do is then we're going to go through every observation in that data A array. In other words, I'm having a loop. And my loop is going to go from 1 to the number of rows in data A. Okay, I don't know how many observations I have. Well, as it happened, that data array for Howells had 310, didn't it? But, I mean, it could be, your station will have a different number of observations. So for every one of those rows, though, that's an observation. Here's a date, here's the high temperature, here's the low temperature. Here's a date, here's the high temperature, here's the low temperature. Alright? For every one of those, again, we saw this slide before, now we've just got the program overlaid over the top of it. I said you should notice the current month and day and year. Well, I'm actually going to have that as part of an if statement here, but I wanted to draw your attention to the fact that data A, row I, column 2, is the year of the current observation I, the one that I'm working on. Row I, column 2 is the year. Data underscore A, row I, column 3 is the month. And data underscore A, row I, column 4 is the day. Okay? Okay, I can see, I could have made, like year is equal to data A, I, comma 2, month is equal. I saved some space here by doing that. Okay, now for every row in our data set that we're working with at Howells, in January, in good data, all that kind of good stuff, that's what's in data A, I now want to go through all the days on my calendar. From j equals 1 to j equals the number of rows on that calendar. Okay? Hey, are you the same date? Nope. Are you the same date? Nope. Are you the same date? All the way through. All those 3,651 rows on that calendar. Okay. Now, what we have to do is notice, are they the same? Now, I actually did this in one giant if statement. You could do it with a little lower tech if you wanted to, like if, and then an if, and then an if. I did it in one. If my data set's year, namely data I, row I, column 2, is equal to dates, row J, column 2. Row J, column 2 is the jth observation, the jth row on the calendar. Column 2 is the year. And data A, row I, column 3, the current month, is equal to dates row J, column 3, which is also a month. And data underscore A, row I, column 4, equals, that's the date, equals dates row I, column 4. What is this and thing? And is exactly what it sounds like. It's and. So if this is true, and that is true, and that is true, then this whole thing is true. Okay? Again, if you didn't want to do it with those and operators, because that seems confusing or something, then make this 3 ifs inside of each other. That would work too, but I'm going to tell you that and is a good trick. I don't know why it's and not just and, but whatever. Well, what are we going to do? If the year of my observation is matching the year of this row on the calendar, and the month of my observation is matching this month on this row of the calendar, and if this date that I might have observation matches this date on this row of the calendar, what am I going to do? Oh, okay. Well, then this is apparently the row of the calendar I want. So my calendar, row J, is equal to my data, which happens to be the one I'm on, data I, comma 5. I, because that's the ith observation I'm on, column 5, the maximum temperature. I know this would have been a hard thing to come up with, okay? That's why it's here. I'm getting you guys to invent the wheel is not the purpose here. You're learning something different that you're going to be seeing in the questions of the project. So giving you this way of kind of filtering out this data, how do I just get that? I'm comfortable giving you that. Okay? Then do the same dumb thing for data B. Okay, you're just going to cut and paste this code in or type it all out again, but you're going to do the same sort of thing where data B is the one you're processing, and you're going to go from I equals 1 to rows in data B, and J goes from, and then if data B is equal, and so on. Okay, you can do this. And when you're all done, you'll have 2 arrays. One's called calendar A, and one is called calendar B. And both calendar A and calendar B have the same number of rows as that array that you read in called, it was the Julian Days array, it was called dates. It's got 3,651 rows in it. And practically all of those rows are just equal to negative 999. Negative 999.9. Because most of them are February's, March's, April's, anything but January. And some of the ones in January are negative 99 because they're missing. But in some of the rows, we have data from both stations, and it is January. So some of those rows, there is a value in calendar A, and there is a value in calendar B. That's the ones we want. Those are the ones that we now have a match. That one is definitely the same observation. That is January 14th, 2010, and this one is January 14th, 2010. Correlate, that's a pair. Find as many pairs as we've got and correlate them. Okay. I experimented with a couple of different ways to make this work, And in my experience, it worked best if I made myself a new array, I called it joint calendar, that put together that calendar A and calendar B into one new array that had 2 columns. Okay? It was just easier to explain. It took fewer lines to explain what's going on here. So let's just make a new array that we're going to call joint calendar. Again, there's fancier ways to do this, but if I just said, hey, it's just I want something that has the same number of rows as dates, but I want it to have 2 columns, whereas dates has 4, I think. What about just say it's dates, all rows, columns 1 and 2? That works. It's a silly little hack, and it worked. Okay, now originally, of course, it's full of other stuff, right? I mean, it's just got those months. No, what does it got? The first column is just that integer that counted from 1 to 3,651, and the second column was years. But that's okay. We're going to put new values on top of that. I mean, what I'm going to do is I'm going to say put station's A calendar into column 1 and put station B's calendar into column 2. So like joint calendar, all rows, column 1 become calendar A. Fill that one up. Joint calendar, all rows, column B become calendar B. Joint calendar, all rows, column 2 become calendar B. Now you've filled it all up. Who cares what the original values are? You've filled it all up with data. You now have something called joint calendar. It's mostly data 999s, but we're getting good at those database operations and those logical indexings. Let's go ahead and get rid of all that stuff. First, filter out all the stations where there's no data in the first column, because either that's not January or that's there's missing data from station A, which happens to be Howells in this example. And then do the same thing, filtering again for station B. So now you have filtered out everything that's missing. Any station any date where both A and B are missing, or A or B is missing, will now be gone. And what you'll have left is a new array. I happen to call mine joint calendar clean. That is the set of the handful of days that are good observations in January. There's both an observation at station A, Howells, and at station B, Hershey. Now I can run my core function. Whew. That was a lot of work. Wait till you run it. It's going to take a couple minutes. Well, at least a minute or so. What in the heck's going on here? Okay, so let's just say I'm going to say R is equal to core, since the simulation for correlation is R. Let's say R is equal to core of this new joint calendar clean array. And like I said, it's going to take about a minute. This is in very sharp contrast to like your other descriptive statistics you've seen so far. When you've been working on this project and you've been computing things like means and medians, you know, the calculation is done before you get your finger off the enter key. I mean, these are fast calculations. How come this one takes so long? It's all those loops. Those loops of that nested loop going over all the observations and then over all the dates just takes a lot of time. It takes about a minute. Holy smokes. A minute's a long time on a computer. Okay. So what actually happened? All right, I run that correlation program. I've set R is equal to the correlation of those arrays. Oh, it's all lovely. Let's display R. Display R, and I've got 4 numbers? That wasn't what I was expecting. What in the heck is this? Well, actually, it's perfect. Remember, that joint calendar clean array, you know, it was 2 columns, and it was all those rows, 3,651 rows, by 2 columns. Column 1 was the station A, and column B was station B. Column 2 was station B. So, that 4 little matrix of 4 numbers that came out, the first one, the top left one, this is the correlation between column 1 of that array with column 1 of that array, which is by definition 1, right? The correlation of column 1 with column 1 is 1.0. It's a perfect correlation. Now, the top row, the right value there, that is the correlation between column 1 and column 2. That's actually what we're looking for. We're looking for the correlation between the data at station A, Howells, and what's in column 2, station B, Hershey. And so, when we correlated the column 1 and column 2, that's what we look for. We got a correlation of 0.76. That's pretty darn good. That's an awfully good correlation. Alright, hey, what are these other values? Well, the bottom left correlation value there is a correlation between column 2 with column 1. But correlation is symmetric. The correlation of column 1, column 2 is exactly the same as the correlation between column 2, column 1. So you get the same value again. And then finally that bottom right value there is the correlation between column 2 and column 2. So you get, again, by definition, 1.0. So see, we got this little matrix, a 2 by 2 matrix. We had 2 columns of data, and we got a 2 by 2 matrix. If we had more columns of data than that, for whatever reason, we'd have gotten a 3 by 3 or 4 by 4 or 5 by 5 matrix. This is pretty slick, and it gave us the value that we wanted. We got a correlation of the high temperatures in January between Howells and Hershey of 0.76. That's a pretty good correlation. In the project, I ask you to do something very similar to this, and then I ask you to do the same thing again, but take out that condition about it being January, and you're going to get a different correlation. I'm saying, now don't worry about what day, forget about whether it's January, March, April, just whatever day, any 2 days that you can match up, correlate them. And you're going to get a way higher correlation than that. And then there's a little essay question there for you to figure out, why was the correlation so good when we weren't looking at like a month of data, and it's nice, but not as high when we were. Oh, it's an interesting critical thinking question. All right, but when you do that year calculation, keep in mind that's 12 times more data, which means if it took about a minute to run your correlation program for 1 month, it's going to take like 12 minutes to run your correlation program for like a year, for a year round. Just so you know, what a huge pain in the butt. That's a lot of calculations. For the record, this is called a correlation matrix. A correlation matrix is one of these arrays that contains the correlation. It'll always have along the diagonal from top left to bottom right, it'll always have 1.0s. We'll see other applications over the course of the semester of a correlation matrix. But why, in the end, why was this so hard? I made 50-some slides about this. Why was this one so hard compared to other things that we have done in this class about how to make different kinds of descriptive statistics? Means, medians, modes weren't so hard. Well, it was this business of matching up the observations that took so long. When you have a data set and you got another data set and you got to figure out how to match up, this one goes with this one and this one goes with this one, that takes orders of magnitude more operation than just like a sum or an average or even like a variance or something like that, because of all the operations it takes to match them up. And keep in mind, in the end, this was only 3,000 some odd observations. I originally had written this assignment wanting you to do something that was much larger for your correlation, but it got out of control. I mean, I don't want you guys waiting 20 minutes for each time you run your correlation and then find out there was something wrong. So, you know, not to mention, like when we did a larger part, this is going to have some bearing on how we plan for our calculations that we're going to do in later projects, okay? Things like matching up observations from different data sets is really time-consuming. Now, admittedly, Octave is not the best tool for the job for something like that, but in general, that's time-consuming. Sorting data is time-consuming. Matching data up makes you wonder how really big data operations like Facebook or Google do it. Well, we'll learn more about that kind of stuff. Keep in mind, this is on Mamaja's core course that satisfies, or should be satisfying, your what did they call it? Certified technology or something like that. And one of the things of certified technology courses is we have to learn about big data and how they do it and what are they doing with it and so on. And what I want you to notice is this was only 3,000 temperatures, and even this was a pain in the butt to actually do all the matching up. Makes you wonder what something like Facebook is going to be doing with all that data that they got from you. All right. Whew. That is a big problem to get all that sorted out. I will let you go and you can put this together. You have one more lecture, I think, maybe 2 before the end of this module, and this is one of the harder parts of Project 2. Alright, please let me know if you have any questions. This has been Dr. John Schrage.